So yesterday you had two videos to watch, kicking off the third module corresponding to Chapter 4, Probability. The first video introduced the concept of probability. So just talked about how we think about events being likely or unlikely events, and how we can put a number on a scale ranging from 0 to 1 that says how likely we believe something is to happen. And there are two kinds of probabilities that we looked at. The first is a theoretical probability. Sometimes, because of how an experiment gets described, we're able to calculate exactly, in other words, theoretically, how likely that event is to happen. Other times, that theoretical calculation is not so easy, and so we collect a lot of data. And if we calculate a probability from observed data, we refer to it as an empirical probability. Most of what we'll do is going to be based on theoretical probability, but we will have at least one example that looks a little bit at empirical probability, just so that you have an idea of what that's about. But let's take a look at our first example here. So when we talk about probability, it's all done in the context of an experiment. An experiment here has a pretty broad definition. You shouldn't just think of someone with a lab coat mixing chemicals. An experiment here means any action that can be repeated, and when you repeat it, you can potentially get a different result. So rolling a die is an example of an experiment, because if you roll a die twice, there's no guarantee that you're going to see the same number come up twice. And whenever we do an experiment, all the possible results that can occur, we refer to those as outcomes. So say you're rolling a die, and it's a standard die. The outcomes that you could see from rolling a die are the numbers 1 through 6. And each of those is equally likely, as long as it's a fair balanced die. If it's not some kind of trick die used by casinos, historically have sometimes like weighted dice so that they don't land fairly, and that's an illegal practice. But there are die that are weighted in such a way that the 6 sides are not equally likely. We're just going to assume the 6 sides are all equally likely. So there are 6 outcomes, all equally likely. And now we're going to investigate specific events. So when you calculate a probability, you're doing it for an event. And so our first event in part A, our event here is that we roll a 6. So what you want to do now is, once you've defined an event, you want to count the number of outcomes that correspond to that event, and you want to count the number of outcomes that there are in total. So how many outcomes of rolling a die actually correspond to rolling a 6? There's only one side of the die that gives you a 6. So there's one outcome that corresponds to rolling a 6. And we know there are 6 outcomes in total. And we write a big P for probability, and then in parentheses, we put the name of the event. We'll often use the letter E. That's what you'll see most often here, just E for event. And we've defined that in this case to be rolling a 6. So the definition of probability that we'll work with most of the time here says the probability is defined as the number of outcomes corresponding to that event divided by the number of outcomes total. And so in this case, that would be 1/6. And when you're doing the homework later on, you'll see the homework will either ask you to represent something as a fraction or it'll ask you to write it as a decimal. This is how you would represent it as a fraction. On the homework, you would just enter 1/6. If I had asked this as a decimal, generally, if we do a decimal here, you'll see it'll ask you to round to 4 places. So the same probability as a decimal would be 0.1667. So just check whenever you're doing the homework, pay close attention whether it's asking for a fraction or whether it's asking for a decimal. Let's look at part B. Our event in this case is that we roll an odd number. So again, we want to count how many outcomes are there in the event E. So how many outcomes are odd numbers? Well, we know it's 1, 3, and 5. So there are 3 outcomes in E that correspond to rolling an odd number. And so the probability of E in this case will be, again, the number of outcomes in E divided by the total number of outcomes. So in this case, 3/6. Now again, if you're doing this on the homework platform, it may ask you to simplify the fraction, but generally it doesn't. So if you just enter 3/6, it should be fine. It's not going to expect you to simplify, but note that 3 and 6 are both divisible by 3, so this is the same as 1/2. So that's how we would express it as a fraction. Either of these will be acceptable on the homework system. Let's look at our third event. Our third event says we roll a number less than 3. So I'm just going to write out the outcomes again. 1, 2, 3, 4, 5, and 6. And I want to identify which of them are less than 3. Well, that's only 1 and 2, right? Because is 3 less than 3? No. This did not say less than or equal to, it just said less than 3. So in this case, the number of outcomes in E is 2. And so when we calculate our probability, it will be 2/6. So you could write that as 2/6, or you could write it as 1/3 if you're representing it as a fraction. Both of those would be acceptable. And our last one here, find the probability of rolling a 7. So our event now is rolling a 7. Well, how many of the outcomes actually correspond to rolling a 7? The outcomes are 1 through 6. There is no outcome that gives us a 7. So that's 0. And so therefore the probability will be 0/6, which is just 0. That is an example of an impossible event. If you roll a standard 6-sided die, it's impossible to roll a 7. So it makes sense that the probability for that is 0. Take a couple of seconds, glance through this example, and let me know if you have any questions here about probability. But our next example is going to be very similar. Okay, so on our next example, we're dealing with a 15-sided die. Now, maybe you've never seen a 15-sided die. That's okay. You can imagine having a die with 15 sides numbered 1 through 15, and we're assuming all those sides are equally likely to be rolled. What's important here is this definition of probability where we're counting the outcomes in an event and then looking at how many outcomes there are total. It is important that we have equally likely outcomes for that definition to hold. So what we do know in this case is the number of total outcomes is 15. Now let's look at part A, where our event is that we roll a 5. How many of the outcomes, and again, I can list the idea of the outcomes. It would be all the numbers 1 through 15. So how many outcomes are there where the die would show a 5 once you've rolled it? Only one. So in this case, the probability is going to be 1 in 15. That's how we would represent it as a fraction. What about part B? Part B says we roll an even number. So now we want to go and count how many outcomes are there in E. Well, you're certainly welcome to go and write them out if that's helpful. We want to know, if we're looking at the numbers 1 through 15, how many of them are even numbers? So I can go and list out all the ones that are even numbers, 2, 4, 6, 8, 10, 12, 14. And there are 7 numbers like that. So the probability of rolling an even number is going to be 7 over 15. And finally, what's the probability of rolling an 11 or a 12? So which outcomes correspond to rolling an 11 or a 12? Just 11 and 12. And how many outcomes did we just list? 2 of them. So here, the probability of the event of interest will be 2 over 15. So I'm going to ask for a thumbs up at this point, just to make sure everyone's feeling good about this. So just hit the yes button on Zoom if you're feeling okay about these probability examples. So let's look at our next example. So here we're looking at just a small aquarium with fish in it, fish bowl. It has 12 red and 8 blue fish. And you're going to close your eyes and get your little fish net and scoop one of the fish out. And if you select that fish at random, we want to know what's the probability that it will be blue. So here, you can go and list the outcomes again. And what you'll see here is, there are 12 different red fish and 8 different blue fish, so 20 outcomes in total. And our event E here is that you choose a blue fish, and how many of the outcomes correspond to blue fish? 8 of them. So the probability of E here is going to be the 8 outcomes that result in you selecting a bluefish out of the 20 total, we want to express this as a decimal, and 8 divided by 20 is 0.4. So that's how we would do this as a decimal. Let's look at our next example. So the National Center for Health Statistics reported that 23.3% of deaths in the United States in 2010 were caused by cancer. What is the probability that a random person who died in 2010 did not die of cancer? So here we're dealing with an example of a complement. Our event E is that someone died of cancer. That's what we're given the information for, right? We are being told the probability that someone died of cancer, that 23.3% as a decimal, I can express that as 0.233. But we're not interested in that probability. We're interested in the probability of not E, that someone who died did not die of cancer. So the complement rule says if you're trying to calculate the probability of the opposite or the complement of the event, you just do 1 minus the probability. So in this case, it'll be 1 minus the 0.233, and that's 0.767. So whenever you see the word not, make sure, typically you're going to see the information provided is the opposite of the probability you're trying to calculate. Like here, we are being given the percentage of deaths attributable to cancer. But we're not interested in that percent. We're interested in a proportion of deaths not attributed to cancer. And so you just apply the complement rule. Probability of not E is equal to 1 minus the probability of E. And we'll have a few more examples like this come up as we progress. So next example gets into a deck of cards. Now, I talked through what a deck of cards looks like in the first video yesterday. So go and revisit that if you're not comfortable with a deck of cards. The deck of cards standard has 52 cards in it, numbered 2 through 10, and then Jack, Queen, King, Ace. And half the cards are red, half are black, divided into suits. Hearts and diamonds are red cards. Spades and clubs are black cards. So in this example, you're taking a deck of cards, you're drawing a card from the deck at random. So the number of total outcomes is 52. That's how many possible cards there are. We want to calculate the probability of the event E that you draw a jack. Now, how many jacks are there in the deck? There are 4 of each kind of card in the deck. So the probability here will be 4 over 52. Again, if the homework system just asks you for a fraction, you can just enter 4 over 52. You're certainly welcome to simplify this a little bit. Both of those numbers are divisible by 4, so this is the same as 1 over 13, or you could write it as a decimal, round to 4 decimals, 0.0769. Let's next look at part B. Our event E is that we draw a face card. Now, which cards are the face cards? Jack, Queen, King. Those are our face cards. And we know there are 4 jacks, 4 queens, 4 kings. So the number of possible cards that we could draw that would show us a face card would be 12. And so in this case, the probability of the event E is 12 over 52. And let's just write that as a decimal. That would be rounded to 4 decimals, 0.2308. Okay, let's look at our next example here. Another example dealing with a deck of cards. Card is drawn at random from a deck of cards. What is the probability that it will not be an ace? So our event E is that the card we draw is an ace. And how many aces are there in a deck? There are 4. So this would be 4 over 52. Again, we can certainly go and simplify that to a decimal, but let's just leave it as is. So what we want now, though, is the probability of the card not being an ace. So the opposite of drawing an ace, not drawing an ace. And this will be 1 minus the probability of E. So 1 minus 4 over 52, which is 48 over 52. And again, you're welcome to go and express that as a decimal if you want. Let's look at this next example. This one comes with a nice little picture. So here you're using the spinner and you want to see where the hand lands, and we're assuming that it cannot land on a line. So it'll be clear which section of the wheel the spinner lands on. Now take a look at the spinner. 2 of the segments are numbered 1. 1, 2, 3, 4, 5 of the segments are numbered 2, and finally 1 of them is numbered 3. So the total number of outcomes that we have here, there are 8 segments to the spinner. In part A, the event we're interested in is that it lands on a 2. How many of the outcomes or how many of the segments of the wheel actually correspond to a 2? If you go and count them, there are 5 of them. So the probability of E is going to be 5 over 8, or as a decimal, 0.625. What about B? Not landing on a 3. So we have an opposite here again. So let's consider the original event that it lands on a 3. And how many outcomes on that wheel actually correspond to a 3? Only 1 of them. So the probability of E is going to be 1 in 8. We want the probability of not E, so not landing on a 3, and that'll be 1 minus 1 over 8, which is 7 over 8, or if you express that as a decimal, you could write it as 0.875. Let's look at this next example. So here someone's doing an experiment, and the experiment consists of two parts. First, they flip a coin, and then they toss a regular die. And we are being asked firstly to list all the possible outcomes of this experiment. And it tells us what kind of notation we can use. For example, if we write H2, that means the coin landed heads, and then when we rolled the die, it rolled a 2. So if we toss the coin, it could be heads or tails, and that heads could be followed by any of the 6 possible numbers. So H1, H2, H3. In fact, let me list all of them. So there are all the possible outcomes from this experiment. And if you go and count them, the number of total outcomes here would be 12. So next, we want to calculate the probability of the event that we get a tail followed by a 3. How many of the outcomes actually give us a tail followed by 3? Only one of them. So the probability of E here is going to be 1 over 12. And if you're asked to express that as a decimal, you would write that as 0.0833 rounded to 4 decimals. What about C, the probability of getting a head and an even number? So which outcomes correspond to getting a head and an even number? It would be H2, H4, and H6. So how many outcomes are there in this event? 3 of them. And so our probability will be 3 over 12, which simplifies to 1 in 4, or you can express it as 0.25. Okay, so the next example says we're tossing a coin 3 times in a row. We want to calculate the probability that if we toss a coin 3 times in a row, we see heads exactly once. Now, if you just look at this question, it can seem pretty ominous. Like, how do we calculate this? Well, anytime you have uncertainty about how to do a calculation, go and list all the outcomes. So list what is possible if you toss a coin 3 times. So even though it wasn't explicitly asked for here, it's to your benefit to go and do that. If you toss a coin 3 times, you could see heads, 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 or heads, heads, tails, or heads, tails, heads, or heads, tails, tails. You can systematically work your way through and list all possible outcomes if you just toss a coin 3 times. And if you list all of them, you'll see the total number of outcomes in this case is 8. Now, we are looking at an event E that we observe heads only once. So now you can run through the outcomes that you've listed and see which of them correspond to only one heads, and by virtue of there being one head only, there has to be two tails. But you can go through all the outcomes and count. There are 3 of them where heads is seen only once. And so the probability of this event is going to be 3/8, or if you express it as a decimal, 0.375. Here's another kind of similarly flavored example. You throw 2 dice. You want to find what is the probability that the sum of the dice will be 8. So the question seems pretty big, but perhaps we can start by listing out all the possible outcomes that could occur. Now, you can go and list them out, first die is a 1, second die is a 1, or first roll is a 1, second roll is a 2, and you can go and list all of them out. But what I find easy to do in this instance is I actually do like a little table. I know with my first die, I can get a 1 through a 6. I know on my second die, I can get a 1 through a 6. And I construct a table specifically in this case because I'm interested in the sum. Like just knowing the 2 numbers doesn't tell me everything I need to know. I want to know what the sum of the 2 numbers are. And so I can go and fill out this table with all the sums. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. So each time I take the number in the row and the number in the column and I add them. Number in the row, number in the column, add them. So let's take a moment here to complete this. Okay, because now when I define the event E, the sum of the 2 dice is 8. I can run through my table and I can identify all the 8s. And how many times do I get an 8 here? 5 times. How many outcomes are there total? Well, how many sums did I calculate? Each row has 6, and there are 6 rows. So 6 times 6 is 36. So we'll just go and count how many sums did you calculate. So the probability of E here is going to be 5/36. And if you express that as a decimal, rounded to 4 decimal places, it's 0.1389. So let's take a quick 4-minute break here, and then we'll pick back up. I apologize. Let me redo this example because I had my mic muted. So I'm really sorry. Let's fix that. Let's just clear all of this so I can talk you through this example again. So when we're talking about odds, we are expressing the same information as in a probability, but we're expressing that information in a different way. So at this point, we could easily go and calculate. So here we're interested in the event we roll an even number, and we can go and calculate that probability. But odds are often used in gambling situations, or it's also how news media tends to report how likely events are, like odds against versus odds in favor of an event happening. So here, the event we're interested in is rolling an even number. For this experiment, we can go and list all the possible outcomes, the numbers 1 through 6, and then we can go and count how many of the outcomes correspond to event E, those are the outcomes in favor of the event, and how many of the outcomes are not in E, those are the outcomes against the event. So we count the number in favor of and the number against. And there are 3 of the outcomes that are even numbers, 3 of the outcomes that are not even numbers. And odds are generally expressed as odds against. So the number of outcomes against is listed first, and then the number in favor is listed. That's just the convention here. So we can say the odds against rolling a 3, rolling an even number is 3 to 3. And so I know the numbers are the same in this case, but it's the number against, I list that first, and then the number in favor, I list second. But also very important, when you're listing odds, you want to make sure the numbers you're listing do not have any common factors. So here simplification is important. What is a common factor? What is a number that both of these can be divided by? Well, they can both be divided by 3, which would give me odds of 1 to 1. So you want to simplify these by eliminating common factors, dividing by numbers that they have in common. Let's look at another example here. We're again dealing with a standard deck of cards. And we're drawing a card from the deck at random. What are the odds against the card being an ace? So our event here is that we draw an ace. And we want to calculate how many outcomes are not in E. Those are the outcomes against. And we want to count how many of the outcomes are in favor. In other words, how many of them are in E. So how many cards are aces? Those are the ones in E. There would be 4 of them. How many cards are left? 48 cards. So we would say here, the odds against drawing an ace are 48 to 4. Now, these have something in common. Those numbers are both even numbers. So at the very least, we know we can go and divide both of them by 2. If we do that, we get 24 to 2. But those are still even numbers. We can go and divide by 2 again. And at this point, it won't simplify any further, but the odds against drawing an ace are 12 to 1. Let's look at the next example here. So here, a sports writer thinks that a specific team has the odds against AFC winning are 7 to 2. And we want to convert that to a probability. Now, if the odds against something, if the odds against event E are A to B, then the probability of E is going to be equal to B over A plus B. That's how we convert odds to probability. In this case, the event E is that AFC wins. Our A in this instance is 7, and the B is 2, and so this will be 2 over 7 plus 2, or 2 over 9, which of course you can go and express as a decimal rounded to 4 places, 0.2222. So easy enough. If you have the odds against as A to B, then the probability of the event itself is just equal to B over A plus B. And now I'll show you how we flip that around. So here's an example where we're given the probability. We're told the US Census Bureau reports that 85% of people in the United States in 2012 were covered by health insurance. So our event E is that a person is covered by health insurance. And we're told the probability of that event, like expressed as a decimal, is 0.85. We now want to convert that to odds. What are the odds against a person being covered by health insurance? Now, odds, you can always think of as a ratio, A over B, and that ratio is equal to 1 minus the probability of E divided by the probability of E. So in this case, if I plug in those numbers, I get 0.15 over 0.85. Now, I need to convert these to whole numbers. So the first thing I can do is multiply by 100 to get rid of the decimal. So I get 15 over 85. So I can say the odds against are 15 to 85. But again, we want to express these without them having a common factor. Now, 15 and 85 are both multiples of 5, so I can go and divide both of them by 5. And so I get 3 to 17. There are my actual odds against someone being covered by health insurance. One way to think about interpreting odds, this may be a useful way to think about it. This says, if you go and you randomly select people in the US and you ask them whether they are covered by health insurance, we're looking at odds against. So we would find, if we find 3 people not covered by health insurance, then that tells us we would expect if we're just collecting people until we find 3 not covered by health insurance, we would expect to have another 17 covered by health insurance. Or out of every 20 people, 3 will not be covered by health insurance and 17 will. Here's another example where we want to convert a probability to an odds ratio. We're told there's a 64% probability that a team will win a game. What are the odds against the team winning the game? So our event E is that the team wins the game. And we're told that probability, the 64%, is as a decimal 0.64. So the odds ratio is 1 minus the probability of the event divided by the probability of the event. So I firstly want to get it as not fractions. So just express it as whole numbers, 36 over 64. So the odds against the team winning are 36 to 64. But I want these to not have common factors. Both of these are divisible by 2. So I can go and divide by 2. And I would get 18 to 32. These are still divisible by 2. You could directly go and divide by 4. If you recognize that as a common factor, that's fine. But 9 to 16. 9 only has a factor 3, 16 only has factor 2. So here we've simplified it as far as possible. So the odds against the team winning here are 9 to 16. Going to skip 4.2.9. It's just, you can go and do that easily. Just list out all the outcomes if you toss a coin twice. I'm skipping 4 to 11 as well. That's similar to what we just did. We have a probability and we want to convert to odds because I want to make sure we touch on house odds. So our last 2 examples deal with house odds, or you can think of it as betting, often betting in sports. So if you go to a casino or if you go to the racetracks, you'll see odds being offered on making specific bets. We refer to these as house odds, and house odds have very little to do with how likely outcomes are. House odds just tell you what the payout is if you make the right bet. And the house odds are typically set up in such a way that they favor the casino or the racetrack wherever you're betting. So if you see house odds, there's still odds against, but they don't actually tell you how likely something is. They just tell you how much money you make if you place a bet. So in this case, the odds against are 2 to 5. And someone is going to place a $2 bet on Seattle Slew in the Belmont Stakes. Seattle Slew went on to win the race. We want to know how much money they won. Now, if you place a bet on something with odds against A to B, if the horse or the event that you're betting on wins, you get A over B dollars for every $1 bet. And you also get back your original bet, your original amount wagered. But if you lose, you get nothing. So in this case, if the horse wins, A to B is 2 to 5. So 2 over 5 is 40 cents. So you will get 40 cents for every dollar that you bet. And you bet $2, so you will win 80 cents. That's how much you win here, A over B for each dollar bet. But just remember, you also do get your $2 back. So you get back the $2 plus the winnings of 80 cents. And we have one more example here dealing with house odds. So 2013, the Las Vegas house odds against the Seattle Seahawks winning the Super Bowl were 7 to 1. If a gambler bet $90 on the Seahawks, how much would the gambler have won in addition to having their wager returned? Because the Seahawks went on to win. So the odds against are 7 to 1, which means you would win A over B dollars per $1 wagered. Now in this case, this would be 7 over 1, or wow, $7 for every dollar that you wagered. So your winnings here would be 90 times $7, or $630. You also get the $90 back. The winnings here are just the kind of the profit that you make off of the bet. So just remember, all you have to go and do is look at the ratio A over B and see, multiply that by how many dollars you actually bet. That'll tell you what you would win if that event were to happen.